is 2.2.1, fields, fluxes, and Gauss's law. Okay, so the past video we talked about how to use the integral of some charge distribution to find the electric field generated by those charges. But you're going to realize quickly that those integrals are going to be very hard. In principle, that we can deal with simple charge distributions easily, but it gets hard fast. So instead of explicitly integrating over all the charges, we are going to introduce a new trick that's going to lead us into Gauss's law, which I imagine you've seen before. So let's first write what the electric field is for a point particle. The electric field at some distance r away from that point particle is 1 over 4 pi epsilon naught q of that point particle, r squared in the r hat direction, right? And normally I have these script r's and the script r hats, but what I've done here is I've put in my charge at the origin. So if r prime is equal to 0, or the 0 vector, that means that script r, which is r minus r prime, becomes r. Right, so that's the reason for that simplification. And if I draw what this electric field looks like for my point particle, that points radially outwards in every direction. Now there are an infinite number of field lines I can draw. I don't have an infinite amount of time, so I draw some subset of those field lines, right? And they go to infinity, right? They never loop back on anything, and they go out forever and ever and ever. Okay. So this point particle that has charge q generates an electric field that permeates through all space. I can calculate some fraction of those field lines that go through some region of space by defining the flux. All right, so you might have heard of the flux before. Basically, I have some surface. I have some field lines going through that surface. I'm drawing them not parallel, but in reality they would be. The red lines would be parallel to each other. And the flux is defined as the component of these field lines that goes perpendicular to that surface, right? So this is going to be the projection of these field lines. So these are the field lines that are coming out perpendicular to that surface, which may or may not be exactly the same as the field lines that are going in. And the flux is defined as the integral over my whole surface of my perpendicular components, right? The easiest thing to do here is just take the total field and dot it with my infinitesimal area vector that picks up only the perpendicular components, and that leaves me with my flux. All right, so what can we do with that? So let's go ahead and use an example of another point particle and calculate the total flux of that electric field going through the surface of a sphere that surrounds that particle. Okay, so I will go ahead and define my coordinate system like this. I will go ahead and put a point particle of charge q there, and I will calculate the flux through a sphere that is also centered at the center of my coordinate system. Okay, so how do I calculate the flux here? I take my electric field for my point particle, which is going to be 1 over 4 pi epsilon naught q over r squared, r hat, and I dot it with an infinitesimal area vector, that is the patch some patch of area on my sphere. Right. What is that? Right, we have to figure out that is in spherical coordinates, most easily represented in spherical coordinates. On the surface of my sphere, let's say my surface, this is not super important, but let's say my sphere has a radius r. Okay. R is not changing, so if I'm going to build my infinitesimal area vector, I need to multiply the appropriate components for my infinitesimal length. That becomes r squared sine theta d theta d phi, and the convention is to point that outwards in the r-hat direction. So we take the dot product of those two, E dot dA. I'm going to have it be a closed integral here because it's over the whole sphere. I'm left with, let's see, 1 over 4 pi epsilon naught, q over r squared, r hat dotted with all of this, r squared sine theta d theta d phi in the r hat direction. All right, the field lines are leaving radially outwards, and that's the same direction as my patch is pointed, so that's good. That means that dot product becomes really easy. R hat dot r hat is 1. We also notice something interesting here, that the r squared from my dA vector and my r squared for my electric field, those cancel each other out, meaning that the flux that goes through a sphere is going to be the same regardless of the size of the sphere. So I'm left with 1 over 4 pi epsilon naught q sine theta d theta d phi. This is the integral over that surface area. All right, integral over the total surface of a sphere gives you 4 pi. So I'm left with q over epsilon naught, which is independent of the surface. Right. If I were to calculate the flux, let's see. If I were to calculate the flux from a particle here versus here versus here for spheres of different radii, those would be exactly the same. All right, so we calculated the flux of electric field lines going through the surface of a sphere. Now what happens if we have multiple point particles that are generating a field? All right, so I know that I can calculate the total field of something by summing up all of the components of those fields, right? The field coming from particle I1, I2, I3, and so forth. All right, and now let's say that the flux for a surface that includes all of those charges. All right, so I have some series of charges. I have a surface that encloses all of those charges. That becomes the sum, I equals 1 to n, of each one of those integrals, ei dot dA. But we already did this integral, right? That is the flux coming from a single particle. Which is the sum of 1 over epsilon naught qi which is the total charge enclosed by my sphere. So if I change the amount of charge enclosed, I then change the flux that goes through my surface. All right. Unless I didn't actually need to specify that that was a sphere, right? I could have had all of these different charges and drawn any arbitrary surface that enclosed all of them. And I would know that the electric field, if I added up all of the components of that electric field that went perpendicular to that surface, whatever that is, I would get something that was related to the total charge inside of that surface. Now, practically speaking, dealing with spheres is going to be much easier, but it doesn't have to be. Okay. So this right here is something you might have seen before. E dot dA is equal to 1 over epsilon naught Q enclosed. This is Gauss's law. This is Gauss's law in integral form. We can go ahead and rewrite that into differential form by taking advantage of some of the fundamental theorems that we used in the past. Okay, so I can go ahead and rewrite this surface integral as a volume integral, all right, using the fundamental theorem of divergences. That gives me an integral over my volume, del dot E d tau. All right, that's what this left side can be. And this right side, I can rewrite my Q enclosed as the integral over all of the volume that contains that all the charges. All right, that becomes 1 over epsilon naught, integrating over a volume of my charge density, whatever that is, times d tau. So that's Gauss's law, rewritten a little bit, but this volume here exists on both sides. All right, I can integrate over any volume I choose as long as it encloses all of the charges. All right, so as long as that is the condition, I can remove those integrals and tell you that 1 over epsilon naught times the charge density is related to the divergence of the electric field. This is Gauss's law in differential form. Okay. Depending on the circumstances, it might be beneficial for us to look at Gauss's law in terms of the integral or the divergence form, and we should be able to be comfortable switching back and forth between the two.